Hi. So I'm going to talk about understanding the structure and activity of fuel cell electrodes using combined electrochemical and non-electrochemical methods. So although this series of seminars or webinars has been about batteries, some of the difficulties and solutions with studying fuel cells is similar to in batteries, so hopefully it'll be useful for people. So just a bit of background about fuel cells. Fuel cells are devices for converting fuel directly into electricity. So you can see the picture at the bottom is a generalized diagram of a fuel cell. So you've got a fuel electrode on one side and an air electrode on the other side, and an electrolyte in the middle, which blocks electrons from going through, which forces the electrons to go from one side to the other, creating the current which can power things. And then typically you have these units arranged into a stack, and that stack can be as big as you want to power anything up to trucks or even planes. So they've got potential for use across a range of applications, from grid scale power to micro generation, because of this ability to stack cells, and the fact that the fuel, unlike a battery, the fuel's stored externally to the device. So just comparing some of their advantages and disadvantages compared to both conventional generation and batteries. So fuel cells are typically more efficient than conventional generation because they're not limited by the Carnot limit. They've got no moving parts, similarly to batteries, which means that they're quiet, and also they don't suffer from the kind of degradation caused by moving parts. They're reversible, similar to a rechargeable battery, as in if you run them forwards, you're converting fuel into electricity. If you run them backwards, you can convert electricity back into fuel, which might be important in the future. So compared to batteries, they're faster to refuel, as in you can refill a tank with your fuel quicker than you can charge a battery. And importantly, the energy storage is separate from the device itself. So with a battery, you're always limited by how much energy it has, by the size of the battery. Whereas with a fuel cell, if you want to have more energy, you just build a bigger tank for your fuel. And also the storing fuel is a lot cheaper than building a bigger battery. So disadvantages: they're expensive versus conventional generation, and in terms of buying the actual device, they're expensive compared to batteries as well at the moment. They're lower power density than batteries or conventional generation, so that's important in terms of things like things which need high power, like cars or drills and power equipment and that kind of thing, which you wouldn't be able to power with a fuel cell, because the fuel cell would have to be too big. And the final disadvantage is that fuels can, in some circumstances, which I'll come on to later, fuels can actually damage the fuel cell. So the part of the fuel cell that I'm going to talk about is the electrode, and the electrode is an important part of the fuel cell because it's the part where the fuel or air interacts with the fuel cell itself and is converted into electrons and ions, which is the reactions that create the electricity, the energy that you can use as electricity. So they're quite complicated structures. They have to be porous to allow gases in and out. They have to be able to conduct both electricity and ions, and they have to catalyze whatever reaction is going on. So all fuel cells have two electrodes. So you've got the air side, which is called the cathode, and the main job of the air side is to split this oxygen bond to convert it into two oxide ions. And although we think of oxygen as being quite a reactive molecule, this is actually quite a strong bond. So in terms of the activity of the electrode, splitting this oxygen bond, finding a material which is good at splitting this oxygen bond is quite difficult. So on the fuel side, if you're just using hydrogen as your fuel, the fuel side is much simpler because the hydrogen bond is not strong. So it's quite easy to do that reaction. Where it gets complicated on the fuel side is if you're using things like methane as fuel. So in some types of fuel cell, you can use methane or even propane, or even people have used diesel as the fuel, and then the reactions get very then the reactions can get very complicated. And also there's other problems to do with the materials that you make the fuel electrode out of are not especially stable, which again I'll talk about later. So in terms of studying fuel cells, and this is similar between fuel cells and batteries, so the reactions in electrodes in both fuel cells and batteries they're quite a lot harder to study than conventional reactions. So on the left hand side, you can see the diagram is a conventional catalytic reactor. You've got your catalyst bed. So you've got your catalyst bed here, your reactants go in here, they're forced to go through the catalyst bed, and then your products come out here. And you've got your sealing here and here, sorry, at the top and the bottom. So that doesn't, if you want to do some in situ experiments, that doesn't affect what you can, being able to access what's going on in here. So with the situation with the fuel cell is quite different. So you've got multiple places where reactants are coming in and products are going out. The reactants aren't actually forced to go through the electrodes at all. They can just go straight in and out. And in fact, when we study fuel cells at lab scale, that most of the reactants don't actually go through the electrode at all. They just go straight through the cell without reacting. So one of the things that you can do with conventional reactors is you can change the size of this bed or the materials in this bed quite easily, and that allows you to do things like work out what's going on with the kinetics of the reaction very easily. In a fuel cell, if you want to do that, you have to physically make a new device, which is obviously a lot more time consuming. And in fact, some of these parameters are quite difficult to control. And in terms of in situ experiments, you have to have your sealing at the sides to separate the anode from the cathode. You've also got to have the whole thing sealed itself, and that makes doing in situ experiments very difficult. Also, the fact that the main reactions are actually going on close to the center here, so you've got the added problem of you've got a whole load of material above the reaction zone that you actually want to look at. So what I'm going to talk about a lot is non-electrochemical methods. So instead of having your your electrode materials in the form of a fuel cell and try and study them working as a fuel cell, you try and get them into more like this form, a conventional reactor, and try and set up the reaction conditions so that it replicates some aspects of what's going on in a fuel cell. So I've got a couple of examples of that. So the first example relates to polymer electrolyte fuel cells. They're a type of low temperature fuel cell, which people will know mainly from things like the Toyota Mirai, which is a fuel cell powered car. But they're also used in there's quite a few other applications emerging and established. So for example, they're used in forklift trucks because one of the advantages I mentioned before is that you can fill up a forklift truck a lot quicker with hydrogen or than you can recharging its battery. And mobile generators. So for example, the advantage of using a fuel cell in them is that they're quiet, they're not polluting, and in comparing to batteries, you can store the fuel, or you can have more energy in terms of stored fuel rather than having to have a bigger battery. And also, if you're working in a university, these things, hydrogen generators, are becoming a lot more popular. So rather than having a hydrogen cylinder stored in your lab, you've got a polymer electrolyte fuel cell running in reverse, generating hydrogen from water. So we've actually just bought one of these for our lab. So the main problem with these fuel cells is that they use platinum, which is expensive and easily poisoned. So just some numbers on that. So global platinum production is about 150 to 200 tons a year. At the moment, almost 100 tons of that is used in catalytic converters in cars, in vehicles rather. But fuel cell cars use several times more platinum than this. So you can see it be very, if you wanted to have every car being a fuel cell car, we haven't actually got enough platinum to do that. We're not making enough platinum to be able to replace all conventional cars with fuel cell cars. And the other problem is that platinum is, well, it's current. This was a few months ago, so possibly that it might be more or less than that, but 30 is not, it's tens of thousands of pounds or dollars per kilogram. So the Mirai has about £1,000 worth of platinum in it. So one of the things that people have been trying to do is they've been trying to finding ways to replace the platinum. So the main thing that the main part of the fuel cell that the platinum's used in is the air electrodes, the cathode. And as I mentioned before, splitting the oxygen bond is actually quite hard, especially in these low temperature catalysts. So finding a replacement for platinum is actually quite tricky. So one of the things that people have been working on is these iron nitrogen carbon catalysts. So basically you get some kind of molecule which has nitrogen atoms and carbon atoms in it. You mix it with some iron and then you heat it up in nitrogen and it forms, well, basically it forms a mess, but people think it has this kind of structure, where the iron is bound to nitrogen atoms in a carbon lattice. So the advantage of this is that it only uses abundant elements and it's low cost. The disadvantages are it has lower activity at the moment than platinum and lower stability again at the moment. And the main problem with these two is that no one actually really fully understands even the structure of these materials, let alone how they work, in order to be able to improve them in any kind of rational way. So at the moment, all the methods of trying to improve them are basically empirical, trying something and then seeing if it makes it better. So the group that I was working with in chemistry, they were trying to find ways to poison the catalyst, to see if that could give them any insights into how it was working. And so one molecule they found that could do it is this nitrite molecule, and they assumed that it was interacting with the iron site and that it was doing this reaction. Let me move this. That it was doing this reaction. So the main problem with that, it gave them some nice results. So they were able to calculate this active site density of 12 micromoles per gram, which corresponds to about 5% of the iron that they put into it. So the main problem is that they had no way of knowing whether this reaction is actually what's happening, and they wanted to know if this molecule was actually interacting with the iron, and it's incredibly difficult to do that in the context of an operating fuel cell. So what we did was we took the electrode material and did what I said before, put it in a conventional reactor so we could try and study it. So the model we started with is what we call the hemoglobin molecule model. So essentially this is similar to the structure of iron and nitrogen is similar to the structure of hemoglobin in your blood, and this is how nitric oxide binds to hemoglobin, and it binds in very strongly to the iron in your blood, which is why nitric oxide is toxic. And so the method we were going to use to study this is called TPD, temperature programmed desorption. So I'll just explain what that is quickly and then I'll go back to this slide. So temperature programmed desorption, you absorb some gas molecules on your surface, and then you flow a gas, an inert gas over your surface, and you increase the temperature. And at some point, as you increase your temperature, the gas molecules will desorb from the surface, and then the inert gas will carry them away. And then that, if you have a detector detecting these gas molecules, you'll see something like this, that as you increase the temperature, nothing's happening, and then all of a sudden the gas molecules desorb and you get this peak, which then goes back down to the baseline. So it looks something like that. And then this allows you to tell, so it gives you things like how strongly these gas molecules are binding to the surface, and it can also give you information about what's going on when these gas molecules desorb. So for example, the first example I gave is what's called a first order desorption. So these gas molecules are just sitting alone on the surface, and then when it gets to the right temperature, they just desorb on their own. So this second example is something called a second order desorption, where you've got different species on the surface, and then when you get to the right temperature, these species combine together and desorb together. And it's called a second order desorption because two things have to happen. So first of all, these species have to find each other and then they have to desorb. So it's second order, whereas this one, first order, because only one thing happens. They just pop off the surface and float off. And so things like the peak shape can tell you which one of those is happening. So if we go back to the hemoglobin molecule, so what we were looking at doing is we were looking at quantifying the number of active sites. So essentially how big this peak is tells you how many active sites you've got. So assuming that this model is correct, you'll have one molecule of nitric oxide per ion. And then when this pops off and you detect it, then the size of this peak will tell you how many nitric oxide molecules and hence how many ion sites you've got. You can measure the activation energy, and you can confirm that we were looking at confirming the mechanism of poisoning and the identity of the active site. So we started off looking at these three different materials. So the iron, nitrogen, carbon, just the nitrogen carbon, so with this iron removed, and just carbon black, which is essentially mainly carbon, and it doesn't have these nitrogen sites. So you can see that the iron, nitrogen, carbon binds far more nitric oxide than the other two, but the nitrogen carbon does still bind some nitric oxide. Carbon black, barely any. So then we took some of this stuff that we'd exposed to nitric oxide and put it in a fuel cell, or made a fuel cell out of it, and we could see that the method of poisoning in both with our nitric oxide poisoning and the way they do it with nitrite is the same. And we could also do things like, so if you look at this temperature programmed desorption, you can see that there's a low temperature peak and a high temperature peak. So one of the things we did was we heated up to about here, so 115, and that gets rid of most of this nitric oxide and just leaves the high temperature peak. And so we could see that because that was still poisoned, so it's the brown line here, then that means it's the high temperature peak, which corresponds to more strongly bound nitric oxide, which was responsible for the poisoning. So there are a few problems in terms of how well these results match up with this hemoglobin model, which we were assuming was what we were going to see. So the first problem is that the quantity of nitric oxide that is desorbed is far higher than what they measured electrochemically that I talked about at the start. So I mean, it's like what, 20 times higher, almost 20 times higher. And even if you just look at the high temperature peak, it's more than 10 times higher. So that suggests that there is something slightly different going on, which we have to try and explain. So the second problem was that from looking at the shape of the peaks, so this is the iron, nitrogen, carbon exposed to different amounts of nitric oxide, and from the way this peak grows as you introduce more and more nitric oxide, we could see that the desorption is second order, which is inconsistent with this hemoglobin model, because this would just be a first order desorption. So the third problem is that the activation energy that we measured, so you can sort of do this plot, and from the gradient of this line, you can calculate the activation energy, and it was only 46 kilojoules per mole. So as I described before, nitric oxide is toxic because it bonds incredibly strongly to iron, and so the desorption energy should be well over 100 kilojoules per mole. I mean, some literature values have it as, depending on the exact structure of the stuff around, could even be 200 kilojoules per mole, which is, so 46 kilojoules per mole is more like a very weak chemisorption. And the fourth problem was that we sent some of this off, some of this poison material off, to be have this technique called Mossbauer done to it, which is very sensitive to the exact chemical surroundings of iron, and the results of that, I'm not going to describe them, but they were basically completely inconsistent with the nitric oxide in the quantities that we were observing binding to iron. So we needed a new model to replace this hemoglobin model. So it needed to have the nitric oxide not binding to iron, needed to be a second order desorption, and needed to have an activation energy in strong physisorption / weak chemisorption range. So I went back in the literature, and so these kind of iron, nitrogen, carbon materials had actually been studied for a while before they were used in fuel cells, and they were actually used. One of the things that people studied them for was for nitric oxide separation. This was back in the 80s, and one of the things that they thought was that nitric oxide was binding in these kind of dimers. So you've got two nitric oxide molecules stuck together on the surface, and so when they dissolve, first of all they separate and then they float off. So that's where you get your second order desorption from. So the diamonds have to separate first and then they can dissolve. So we thought we'd go with that, as it seemed to fit these three criteria and had been observed before. So, and yes, the other thing is that these are actually, although back in the 80s they didn't manage to work out exactly what the iron was doing, because they observed that you ended up with far more nitric oxide if you had iron, but they never actually managed to work out why. But they did hypothesize that the nitric oxide was binding to the carbon, so we assumed that as well. And so the consequence of that is that it implies that because the nitric oxide is binding to the carbon, that means that the carbon must be important for the oxygen reduction reaction, so the splitting of the oxygen bond. So then we use the same technique, temperature programmed desorption, to look at how oxygen was interacting with the material, to see if we could get any insights into how the carbon was affecting the oxygen reaction. So the first thing we saw, so you pass oxygen over the material, and then you switch to an inert gas, and then you heat it up, as I described before. And then as the temperature increases, then the first thing we saw is that almost all of the oxygen is not coming off as oxygen, it's coming off as carbon dioxide. So that was kind of interesting. It means that the oxygen's binding very strongly to the surface, so strongly that it doesn't just form oxygen and come off the surface as oxygen, it's coming off as carbon dioxide, taking a bit of the surface with it, obviously. And so people have studied what these different temperature carbon dioxide comes off with graphene and graphite before, and so this range corresponds to oxygen in the form of epoxides, ethers, and alcohols on the surface of the carbon, and this kind of temperature range is more carboxyl groups. So the fact that the oxygen dissolves as CO2 means that the carbon surface is worn away. So you can see here, these are oxygen molecules on the surface. And when they dissolve as carbon dioxide, and they leave little, well, this is what we're hypothesizing, they leave little holes in the surface. So then we thought, okay, so if we repeatedly expose it to oxygen, and then dissolve the oxygen as carbon dioxide, leaving these holes, eventually we're going to end up with all the active surface worn away. And we thought that might be quite a good way to study what was going on. So we did that. And you can see that here, that you start off with quite a lot of CO2 being dissolved. And then as you do this cycle of exposing it to oxygen, heating it to 300, and going round, so 24 times in the end. And every time you expose it to oxygen, then heat it, and then re-expose it, the amount of carbon dioxide coming off goes down and down. So that kind of suggested that we were on the right track, that this carbon surface was being worn away, and you were ending up with fewer active sites that could bind oxygen. And we got some of this cycled material and we put it in a fuel cell, and we found that it was actually being deactivated electrochemically as well. So that kind of suggested we were on the right track, that we were removing these active sites. But then there was another problem. So at the end of all these cycles, we heated it to 600, and then we saw this. So that just huge amounts of carbon monoxide and carbon dioxide being given off in the cycled material compared to the uncycled material, which are these two solid lines. And then when we take this material that's been cycled and then heated to 600, and then re-expose it to oxygen and heat it to 600 again, we see it's gone almost back to how it was at the start. So that implies that the cycling isn't removing active sites after all. So something else is going on. So we came up with this other new model. So when we heat up to 200 or 300 when we're doing the cycling, some of the oxygen comes off as CO2, removing some of the carbon, but some of it actually binds in forms that isn't dissolved at 200 or 300 degrees C, and this builds up on the surface. So if we go back to here, you can see that the amount of CO2 being emitted is going down with each cycle, but this isn't actually because the active sites are being removed, it's that they're being blocked by oxygen, which isn't being removed by the cycling. And then these peaks that you see in the cycled material, when we go up to 600, they're all the oxygen that's the tightly bound oxygen which is built up on the surface coming off, and then you can see that how the surface is back to almost back to how it was. Obviously, some of the carbon has gone, but mainly goes back. And then we put this material in a fuel cell, and we could see that similarly to what we saw with the TPD, the electrochemical activity had almost gone back to how it was originally. Not quite, but almost. So this led us to another new model, which is that instead of irreversibly removing active sites by cycling in oxygen, the oxygen is actually modifying the surface in a way that reduces the activity. So this made us think, is the original sample that we're testing already poisoned? Because obviously already poisoned by oxygen, because obviously when you make this material, you don't think of storing it under nitrogen or anything. It's quite stable, so people had just been leaving it lying around in air. And so what we did, so when we thought this might explain the discrepancy, that the reason why less nitric oxide is binding in the electrochemical measurements compared to the TPD is because we actually in the TPD we heat it up to 600 degrees before we do the experiment. So we thought we were doing that to get rid of all the water and anything else that had built up on the surface, but it turns out that maybe actually what we were doing is getting rid of all this oxygen that was poisoning the surface. And so when we do it without this 600 degrees cleaning step at the start, then the amount is much more similar. So we measured 18 micromoles per gram, whereas before it was over 200 micromoles per gram. And then to test this, we did the same thing, but in a fuel cell. So we took some of this iron, nitrogen, carbon. We heated it to 600 in argon, which is our cleaning step in the temperature programmed desorption. And then we ran over to chemistry, made it into a fuel cell electrode as quickly as possible and tested it. And you can see that actually it was much better than the material, so than the material which had just been stored in air. So then that shows that the material is actually being poisoned by oxygen on building up on its surface. So then we thought, so we can remove the nitric oxide thermally, as we do in the TPD, or electrochemically, as they did, as I talked about right at the start of this example. Can we do the same for surface oxygen? So we already know we can remove surface oxygen thermally, but can we do it electrochemically in the same way that we can with nitric oxide? So what we did was we put the material in a fuel cell, and we ran it as a fuel cell, and then every now and then we would just run it in minus 0.3 volts for different amounts of time, just to test, and with the idea that that would remove the oxygen. What we see is that the performance goes up massively as this oxygen that's built up on the surface is removed, and then gradually the surface gets poisoned again, and then we can go back down to minus 0.3 volts and it removes the oxygen again, and again it gets poisoned gradually over time. So that's where we've got with this so far. Unfortunately, we didn't haven't worked out whether the iron is the active site, which is what the original idea of the experiments was, but we have worked out a whole load of other stuff. So so we can say that the nitric oxide doesn't mainly bind to iron, it binds to carbon. So oxygen also reacts with the carbon surface, and oxygen and nitric oxide bound to the carbon surface reduce the activity of the material, and these can be removed thermally or electrochemically, and this restores the activity. So we still have some outstanding questions with this. So one of them is that the reasonable agreement between TPD and electrochemical measurements on the amount of nitric oxide absorption. Is it a coincidence, or is it actually showing that we're measuring the same number of active sites? Why is the activity not fully recovered when the cycled sample is heated to 600 degrees C? So obviously that we're removing some every time you cycle, you're removing some of the carbon as carbon dioxide. So is it not fully recovering because some of the carbon has gone, or is it not fully recovering because it's changing something else about the structure of the material? What is the role of iron, which we didn't manage to work out? And is it possible to modify the surface to protect from attack by oxygen? So I think I've got a bit of time to quickly go through the second example. So this example is on a different type of fuel cell, which is called a solid oxide fuel cell. So solid oxide fuel cells are high temperature fuel cells. So they're currently beginning to be used in stationary power and combined heat and power applications. So the main advantage of solid oxide fuel cells is that they have very, very high efficiency. So that's why people want to use them for these applications. And they can also use carbon-based fuels. The disadvantage of them is that they're high temperature. But despite the high temperature being 600 degrees C or more, but despite that, people are also working on them for transport applications. So the main problems with these fuel cells at the moment are degradation and poisoning. So you can. This is actually a fuel cell, a sort of pilot plant fuel cell. I think that's 200 kilowatts in Japan. So solid oxide fuel cell fuel electrodes are quite complicated because they've got because the reason why they're called solid oxide fuel cells is because they conduct oxide ions, and oxide ions are quite hard to. There aren't a lot of materials that do that efficiently, so it's difficult to find materials that can conduct oxide ions and also electrons. So normally you use a mixture of nickel, which conducts the electrons, and another material which conducts the oxide ions. So normally one of the main parameters of interest in a solid oxide fuel cell fuel electrode is TPB, which is the triple phase boundary. So the boundary between the ionic conductor, the nickel, and the gas phase. And that's where the reaction happens. So one of the main new materials that people are looking at, well, not so new anymore, but one of the materials that's in development is for commercial use is CGO, cerium gadolinium oxide, and that's actually a mixed conductor. Has very high ionic conductivity, but it does also have some electronic conductivity. And what that means is that this the reaction can actually take place away from the triple phase boundary. But because the electronic conductivity is quite limited, we don't actually know how far away from the triple phase boundary that can occur, and it's difficult to separate the two different reactions to get an idea about that, and it's difficult to model as well. So one idea that we came up with was to look at methane reaction on the surface. So because methane only reacts on the nickel, that could allow us to separate the triple phase boundary and double phase boundary processes. So what we did was we pulsed methane over the sample. And you can see that when you pulse methane over the sample, it at 600 degrees C, it converts into, so this is hydrogen. So the unreacted methane is here. You get lots of hydrogen, you get lots of carbon monoxide. You also get a little bit of carbon dioxide and a little bit of water. So we could see that the main reaction is what's called partial oxidation. So that's conversion of methane into carbon monoxide and hydrogen. And there is a little bit of full oxidation, which is obviously the complete conversion of methane into water and carbon dioxide. So when you do multiple of these pulses over the same material, actually I should say that so where the oxygen is coming from is actually the CGO. So what happens is the methane is reacting on the nickel, and then oxygen from the CGO is going to the nickel and either fully or partially oxidizing the methane. So as you do subsequent pulses, the total oxidation almost totally disappears. So in the second or third pulse, you stop getting the total oxidation. So we figured that total oxidation is associated with more oxidizing sites on the surface, which disappear after the first couple of pulses, or are used up rather. And then this happens if you don't have the nickel, that after the first couple of pulses, there's no reaction between the CGO and the methane at all. So the other thing we started noticing, is that from the third pulse onwards, you start getting this very long tail of carbon monoxide as carbon monoxide gradually comes off over quite a really long period of time. So it's almost 2,000 seconds that you've still got after you finish passing the methane, you're still getting carbon monoxide production for 2,000 seconds. And so that we assume that's migration of oxide ions from the bulk of the CGO to the nickel surface, that they're being quite slow arriving at the nickel surface. And then if we do the same on nickel YZ, and YZ can't supply oxygen to the nickel surface, you don't get any tail, you can see in these ones. So if you do it so that if you do the pulses close enough together so that this tail is still going down when the next pulse arrives. So if we did, instead of doing this next pulse here, we did it here, then you do a temperature programmed oxidation which is where you heat the material up in oxygen, then you get carbon dioxide, which shows that this is carbon built up on the surface of the nickel, which is waiting to be oxidized. So we also found that it was quite easy to reoxidize it with steam, and then when you reoxidize it with steam, then the methane conversion returns to its original state. So you can see we do these pulses, and the amounts produced go down and down, and then you reoxidize with steam and it goes back to how it was originally. So from all these results, we worked out that it's the mechanism of the reaction is what's called a Mars van Crevelen mechanism, which is where the two different reactants are where the methane is reacting on the surface of the nickel and the oxygen is coming from the CGO rather than, so even when you have steam in the present in the gas phase, when the methane pulses come, you still see that the oxygen is coming from the CGO rather than from the steam in the gas phase. So the other thing we could do with this technique is we could measure the how the stoichiometry of the CGO is changing as we do these pulses. So because obviously as we do the pulses, the oxygen is coming from the CGO and that oxygen is not replenished. So gradually that becomes more and more reduced. And we can show that the what's going on with the reaction is highly dependent on the oxidation state of the CGO, which has important implications for if you actually want to run these fuel cells on carbonaceous fuel. You need to be careful how reduced this is, because if it's too reduced, then the reactions will be very slow and you'll end up with poisoning your fuel cell with carbon. So the final thing we did in this was we actually took it over to physics, where they have an in situ Raman, and we did the pulse experiment in their in situ Raman, and we could, so the Raman allows you to monitor the surface oxygen in the CGO, and it seems to confirm that the limiting step for this tail of CGO, the tail of carbon monoxide production I talked about, is oxygen migration from the bulk of the CGO. So you can see that the surface is so very quickly depleted of oxygen when the pulse comes, and it quickly at first and then more slowly returns back to how it was as the oxygen migrates from the bulk to back to the surface. And then you can see that once you've done a few pulses, then it doesn't recover back to how it was, because the bulk of the material is also becoming depleted in oxygen. So we're currently working on various other things using this technique. So we're looking at what happens if you age the material, what happens if you use metals which react less well with methane, and we're trying to model what's going on in these pulse experiments so we can get some idea of what these results actually mean, because they show something is changing in terms of how the material interacts with methane as you age it, but it's very difficult to work out what it is that's changing. So we're hoping by getting some kinetic modeling we'll be able to work it out. Okay, so I think that's just in time. So thanks for listening, and these are my co-collaborators. So the SOFC work is this Dr. Mengzheng Ouyang, who it was his PhD work, and Rob and Leslie Cohen from physics, and on the PEM work. So the guy who first came to me to ask me to do the PEM work was Daniel, and then subsequently I've worked with Azad, and then the Mossbauer was these guys. So thanks for listening. So right now I've got to work out how to do the Q&A. Right.
Hi. So just wanted to do a quick reminder that if anyone did have any questions, then you can ask them now. But if not, then